Hello guys, and welcome back to my Applied Data Science channel. My name is Joanna, I'm a senior data scientist, and today I would like to perform together a random forest regression to predict the prices of apartments. This is the second video in the series Data Science in Real Life, where nothing works on the first try. We are trying to distance ourselves from university projects and get a real intuition into what's going on in the head of the data scientist when working with real data on real projects. So let's see what the roadmap for today is. As I said, we are going to predict apartment prices by using a random forest regression, and this comes as a follow-up of previously trying to fit and predict prices of apartments by using a linear regression model. The best metrics that we've recorded with a linear regression was a mean average error of 18,600 euros and a root mean squared error of 23,400 euros. So what we are going to try and do now is beat this best linear model, and let's see if that's possible. First, I'm going to just import the libraries that I'll be working with, and that's Pickle for loading the data and for saving my best random forest regression model respectively. Then for data manipulation, we'll use pandas, numpy, and then we'll also use label encoder in order to encode some of our variables from string to numeric. Then in order to perform the random forest regression, we need to import the random forest regressor. And also here we are importing the metrics that we are going to use to assess the performance of our model and to compare it against the best linear regression model that we've previously trained. So here we are going to use a common set of metrics. And then for visualization, we'll use Seaborn and PyPlot. So the first thing that we'll do after importing the data is do some data sanity check and data processing. Then we'll generate the train, respectively the test sets. Then we are going to actually model our data by using this random forest regressor. And of course, we are going to also do the performance evaluation based on the previously mentioned metrics and reiterate in order to improve the results if that's required. Okay. Here I'm going to start by importing my data set, which is stored in a pickle file, the same pickle file we used also in the linear regression model. And we can import the data directly into a pandas data frame. We are going to read this file as a binary, as f, okay, and now we are going to, and here we are going to define the name of our object, of our data frame, where we'll be storing the data, and by using just pickle load, we can load the data set. So now let's check the shape of our data set. So we will have 161 rows and 11 columns in our data. Let's see exactly how our data frame looks like by printing the first 3 rows. Okay, so this is our data frame. Please allow me to just insert here some cells. Okay, so this is our data frame. We have the variable price in euros. This is what we are trying to predict. This is our response variable. And then we have all the predictors that we can choose to include in our model to improve the predictions. So number of rooms an apartment has, its size in square meters, number of bathrooms, number of terraces, whether it is a pass-through apartment or not, so if you go from one room to the other, or if each room has separate entrances. Then whether the apartment was finished, or it needs renovation, or it's not finished, the neighborhood, the year the building was constructed in, whether it is a central whether the apartment is in a central zone of the city or outside the city center, and the level at which the apartment is located. So these are our variables. The first thing that I'm going to do is check the data types of the variables. As we can see that some of the variables are numeric and other are categorical. And indeed we see here that, okay, the price in euros is an integer, the number of rooms as well, the size of the apartment, numerical, okay, the pass-through is Boolean. And then something that I want to mention is that we have these object variables. First I'm going to start with lowercasing the values. And now let's check that our values are now lowercased. Okay, that's true. So the next step that we are going to perform is encoding by using the label encoder. So first we are going to initialize the label encoder. And now we can apply the method fitTransform on our variables in order to encode them into numerical values. So now all our string variables are going to be numerical variables. And if we print again the first rows of our data frame, we now see that instead of having string values in the neighborhood, in the finished, or in the zone columns, we have numerical variables. And if we check the data types now, we can see that actually these variables, finished, neighborhood, and zone, are integer variables. We are going to have to convert them into categories because they are not actually really numbers or numerical variables. They are actually numerical labels which encode categories. So we must tell our algorithm to treat them properly. Then I'm just going to change the method that I'm applying on each one of these variables, and that's going to be as type now and category. So this way I can convert each one of my variables into categories. Okay, and now let's see if that was completed and if our variables are now categories. And indeed they are categories, and at the same time if we look at the data head, they are categories, but at the same time they are numerical values. Okay, so with this we've finished the pre-processing of our data. Now that we've transformed our variables to the corresponding data types, I would like to also have a visual intuition into how the variable values look like. So for this I'm going to use the pair plot and just pass in our data frame with all the variables in it. Okay, so after 25 seconds we have our pair plot. In the pair plot on the diagonal we see the histograms, respectively the bar charts of each of our variables, depending on the data type that variable is. So for continuous numerical variables, we are going to see histograms. This is the case for the price in euros, also the case of the size of the apartment in square meters. But then for the number of rooms, for example, the data is numerical discrete, so 1 room, 2 rooms, 3 and 4 rooms that the apartment might have, and for that we have here a bar chart. And that is also valid for our Boolean variables, where we only have, for example, true or false. We also have bars corresponding to each one of the classes. The reason why I wanted to display the pair plot is to check if we have any points which have the potential of being outliers. I will double check that by using a box plot. So this is a data frame, and on my data frame I can apply plot directly by specifying the kind of plot that I want, and that's going to be a box plot, sorry. Not a bar plot. Okay. Indeed, I can see that I have 3 points which have the potential of being outliers, and these are the points representing very expensive flats. So now I could either identify these very expensive flats, like the top 3 most expensive, and eliminate them from my data set. And this is exactly what I'm going to do. So I'm going to take the price in euros. And this is going to give me a pandas series. And now I'm going to sort the values. This is going to sort it in ascending order. So what I can do is simply take the most expensive 3 indices, and I'll do this by taking the last 3 values from here. So like that, I'm just going to select the last 3 values. And now step by step I'm going to access the indices of these 3 values. And now I'm going to put these indices inside a list, and these are going to be my top outliers, I'll call them. And now if I want to list them, you can see that here I only have a list with the indices in the data frame which belong to these very high priced apartments. So if I want to drop from my data frame these indices, then I'll just use the drop method, and now I can check the length of my data, and this should be 158, yes, because we've removed 3 outliers out of the 161 rows. Okay, so now the next step after removing these outliers is to prepare my data for training. And the first thing that I'll have to do is decide which is going to be my response variable, and that is going to be the price in euros. So I'm selecting this column as my y variable. Then in the x variable, I'm going to put all the columns that I want to use as predictors. So in order to access their name, I can just say data columns, and now I can copy paste from here all the column names, so I don't have to write it by hand. Here we have 2 options to approach this problem. So we can either start with all the variables and then exclude them if they're not so important for the prediction, or we can just start with a lower number of variables and then try to improve the model by adding 1 variable at a time. So for now, what I'm going to do is just start with all the variables and then see how we go from there. So once we've decided which is going to be the response variable and the predictor variable respectively, we are going to split the x and the y in two sets, the training set and the testing set. This is a package that I haven't imported. So from sklearn model selection, we are going to import the train test split. So this is the method we are looking for. And the train test split is going to take as input the x and the y variables, and then we are going to set a test size. That's the percentage of observations from our data set that are going to be reserved for the test set. So if we choose here, for example, a 0.1, this means that 10% of our 158 observations, that's like 15 or 16, will be kept aside for testing. And now we are going to define the names of the resulting objects. So we are just going to keep things classical and say xtrain, xtest, and then the labels will belong to the arrays ytrain and ytest. Now if we want to check the length of our test set, we can just count how many labels we have in the ytest, and we have 16 observations. Yes, so 16 observations will be kept for testing purposes. The idea behind random forest is to build multiple models, multiple small models, and then aggregate the results from these multiple models in order to improve the overall accuracy and robustness of the predictor. And these multiple models are classification or regression trees. We are here in the regression scenario, so the random forest regressor is going to build a number of trees that we can specify with one of the hyperparameters inputted here, and each one of these trees is going to be built not on the entire data set but on a sample data set which is obtained by randomly sampling from the entire training data set with replacement. This is called bootstrapping also. So for each tree, the algorithm is going to bootstrap a number of observations that we can also set in here. And then besides sampling observations to build each tree, it is also going to sample only a set from the entire set of predictors that we use. So in our scenario, in our case, if we've used all the columns as predictors, so we have here like 10 or 11, 10 predictors, the random forest regressor is going to sample like 3 or 2, whatever number we specify, from these predictors, and then build the tree only with those predictors. So there are actually two sources of randomness in building each tree in the random forest. One source is coming from sampling observations from the data sample, and then the other source is sampling predictors from the set of predictors. And then multiple trees are built, as I said, and the final output of the random forest is going to be an average. Now let's see how we can put all this information into the hyperparameters of the random forest regressor. So the first thing that I said is that we can choose how many trees our algorithm should build before outputting a prediction. And this is going to be the n estimators. The parameter n estimators by default is 100, but we are going to set this, for example, to 500, just choosing a number. We can experiment with multiple numbers. So next we can specify how many predictors should we sample from the entire set of predictors when building a tree. So this is going to be the max features parameter. So max features, we can set this, given that we have in total 10 features, we can specify this to be 3. So when building each one of the trees, randomly sample without replacement 3 of the features in our entire set of features, and then build the model. The next thing that we can specify is how many observations should be sampled when building each tree. So this is the second source of randomness, and these are sampled with replacement, and that's going to be the max samples. Okay. The maximum number of samples that should be used to build our subsets is going to be 60, let's say. Then we can also set the OOB score to true. This out-of-bag score is nothing else than the R squared, indicating the goodness of fit of our model. We are ready to fit the model. On our training data, here are the predictors and here are the labels, because the random forest is part of the supervised learning paradigm, and we are going to store our model under the RF name. Okay, let's fit the model. The model has fitted, and now we can use the RF out-of-bag score in order to check the goodness of fit of this random forest regressor. So we see that the R squared is 67%. We can print this more beautifully. The next thing to do is inspect which variables were truly important in modeling our data. We can access it by using the feature importances. And we see that here feature importances is a NumPy array with all the scores, all the importance scores, which are nothing else than percentages. So if we sum them up, they will all sum up to 1, sorry, to 0. So this would be 100%. And we also have the feature names, and they are accessible features under feature names in, okay, feature names, okay, here. So here are the labels for the previously showed feature importances. So now what we can do is just create a bar plot. The size of the apartment in square meters is the most important predictor for the price of apartments. And then on the second place, we have the number of rooms that an apartment has, and then the number of bathrooms, and so on, with the least important variable being whether the apartment has separate entrances for each room, or the rooms are passed through. Okay, so now the next thing that we want to do actually is evaluate the performance of our model on new unseen dataset. We are going to use our random forest regressor and the predict method in order to predict the prices. And we can store these values under the predicted price name. So this is the predicted price. At the same time, we also have the true price of these particular apartments, which are nothing else than the y-test prices that we've stored previously. And in order to evaluate the performance of our model, we are going to compare these two prices, the true real price of the apartments and the predicted price of the apartments. We are going to use the same two metrics that we've also used in evaluating the performance of the linear regression, in order to actually have a common ground for comparison. The mean absolute error takes in as parameters the y-true, that is our y-test, and the y-pred, which is the predicted price in our case. So this is the mean absolute error. We see that the mean absolute error is 20,000. So this is still 20,000 euros. It's still higher than our best linear model. That's no problem, because at least we have to improve the model. So we'll go over to iterate. Okay, so the mean squared error is taking in exactly the same parameters, the true price and the predicted price. We are not going to print this, but then we are going to use the root mean squared error. So the mean squared error is the base to calculate the root of it, and we are going to report the root mean squared error, because this is a metric that we reported also in the linear regression model. Okay, so if it were to compare our results of our first model against the results of the best model that we have, the conclusion is that actually our random forest regressor performs worse. That's not a problem, because what we have to do now is to reiterate. Okay, so one thing that we could do would be change here the variables that we are using. So we could, for example, remove some of the variables that were not so important based on the variable importance plot. Okay, so let's only keep 5 variables for now. We see that the variable importance has changed. Okay. And now let's see if our reduced model is performing a bit better. No, it is not. It is actually performing a bit worse. The next thing that I would like to do based on the pairs plot of my data is try to logarithmate the response variable. The values are like ranging from 50,000 or even less than 50,000 euros to more than 300,000 euros. So probably by rescaling and bringing to a different range these prices, we could actually improve our predictions. the first thing that I want to do is overwrite the price in euros. Actually, not overwrite it, but create a new variable, price in euros logarithmated, by just logarithmating the price in euros. Okay, so now here we have to change our response variable to take into consideration the price, the logarithmated price in euros. And now we are going to split our data set and check the out of bag score. We see that it has improved. Now it's 0.69. The variable importance looks pretty much the same. And now we must keep in mind that the predicted price and the true price are on the logarithmic scale. So in order to have similar comparison, we'll have to exponentiate the values. So we'll use numpy-exp in order to exponentiate the values and report the sums in euros. Now we can see actually that our values have increased even more, so this is decrease in performance. One thing that I would really like to check is exactly how far off are my predictions from the ideal predictions. Okay, so here is what I meant. So I can see exactly how far off are my predictions. Those are the orange points from the true prices. And I can see that here in the upper right corner, my algorithm has the tendency of underestimating. So it is predicting lower prices for the very expensive apartments. So currently I have the prices on the logarithmic scale, and to get a better intuition into their meanings, I'm just going to change that to the absolute value scale. Okay, so now I can see actually that the differences are very large. For example, I'm predicting around 150,000 euro price for an apartment costing above 250,000 euros. So actually this very expensive flat having such a low predicted price is adding up a lot of error to my metrics. So one thing that I could go and do is check exactly what's the matter with this apartment. Is my algorithm truly like that bad, or is it a problem with this sample from my test set? I have one suspicion that is actually causing the algorithm to under-predict for very expensive flats, and that has to do with this one suspect data point that I have over here. Because here I can see that these really big apartments, there are like 3 data points here with really big apartments, and one of them has an unusually small price. So what I would do is identify exactly what's that data point and then just eliminate it from the data set. Okay, so I want to select that data point for which the size of the apartment is approximately 100 square meters, so it's going to be larger than 95. This is the first condition, and then the second condition is that the price is also around 160. Let's see more exactly. Below, let's see if we put it below 200. We have one apartment. This is our outlier data point that we keep seeing here in the plot. So this point here is actually observation 121, which I want to delete from my data set. Now let's go back to our normal price in euros. Calculate the out-of-bag score. We see that it has improved. We are only working with the same set of variables. Okay, so let's predict the price. And now, because we are working with the price in absolute values, not the logarithmic price, we are going to run this cell over here. Okay. Sorry. So finally we have an improvement in the mean average error already. By removing this outlier, we can see that the situation has improved. Given that I have so few data points in my data set, I would like to even lower the test size more and maybe just see if that improves on the results. Okay, so I can see actually that my results have improved when I reduced the test size. And this can be also because now I'm not allowing, yeah, of course. So these are better results because in my test data set there are not so many very expensive apartments. So for these apartments, actually the algorithm is performing well, but I don't know what would happen once I'd, for example, include more expensive apartments in the test set. Yeah, so probably the performance would continue to decrease. So this problem can be solved by performing cross-validation. So in cross-validation, what you're doing is splitting your data set into train and test multiple times, each time in different sets, and then running random forest regression on each of these different data sets and evaluate all these different models. Indeed, I got much better results when I removed that one particular outlier. So basically that outlier was probably messing up with my random forest regression, and just by removing that one outlier, I managed to improve the mean average error and the root mean squared error, such that currently I already have a random forest regression that's performing better than what we have up here as the benchmark, the best linear model that we've trained. So now what I could do is save this model for later use. And I can do it by saving it in a pickle file. I'm going to call my pickle file random forest for apartment price .pickle. And I'm going to open this file as a binary that allows to write in it, okay, as f. And now I can use pickle dump to simply dump my model in this particular pickle file. What this is going to do is create here a pickle file, which is called exactly as I called it here. And now I can open this pickle file and just use it wherever in order to predict. That's it for today. We've reached the goal to outperform the best linear regression model that we've previously trained on our dataset, and now we have a better model to predict the prices of apartments with. In the next few weeks, I'm going to show you how to turn your machine learning model into an application that can be used by anyone with a very simple user interface, where someone could come in and input the characteristics of their apartments and then calculate which would be the market price for this particular apartment. So I hope you are excited for these next weeks that we are going to learn how to turn our model into an API, and then how to deploy this model and how to create such an application that actually has our model in the background. And hope to see you next time. Bye bye.